Okay, we ever take a tricky integral. This one's from the UNSW Integration Bee 2024, round 2, problem 15. We have the integral from 0 to infinity of cosine pi, the floor of x over the floor of the ceiling of x to the 1 over 2024th power dx. Okay, to get started, the first time through on this, I wanted to do the usual thing, just looking at the floor we have right here. What I usually do is break up the integral on integer bounds, like going 0 to 1, 1 to 2, 2 to 3. That's going to be fine for simplifying the numerator, but the denominator is actually kind of more complicated, and so I think I want to just focus on this part first. So to simplify this a little bit, what I want to do, instead of looking at everything we have going on here, let's just look at x to the 1 over 2024. We're looking for points where we're going to get integers where we can get simplification, just like if the problem was this and we want to break up our bounds to simplify this, I want to do something in order to simplify this. And for this, we just noticed that we're going to get nice integer value. We're going to get nice values if we have something like, if I have 2 to the 2024 to the 1 over 2024, then this is just 2. And then the same thing with, 3. We could go through this, but anything like this, anything like a to the 2024 is just going to give back a when we put it in this power here like this. Now, when things get a little more complicated, though, when we've got like the ceiling function on the inside, raised to a power inside the floor, there's like a lot to kind of unpack there. We just have to get a feel for that. Maybe to make it a little easier to look at, let's kind of pretend instead of having 1 over 2024, let's make it a little simpler and have it like the ceiling of x to the 1/3 and what happens with the floor of this. And just imagine this thing's in some kind of integral and we're going to break this up. So using this idea, if I wanted to break up something like this, then I would say let's go from 0 to 2 cubed, which is 8, right? And then for the next one, we'd be going from 2 cubed to 3 cubed, and we just kind of keep going on and on like this forever. Now, if you try some different values between 0 and 8 and plug them in here, if you put in like 5, it's going to be going to 1, or anything really is going to 1. Now, where there's a problem, though, if you look at, let's just say x is like 7.5. First, because the ceiling function's on the inside, the ceiling is going to round this up to 8. We take the 1/3 power on 8. Now we have 2. The floor takes us down to 2. So for that case, actually everything between 7 and 8, this doesn't work. We're going to get 2 there. Well, what I can actually do to fix this, just to adjust this so we don't have this problem, I can just if I subtract 1 on this bound, this here now is 7. And now if you plug in values, everything from 0 up to 7, not including 7, all that's still going to be 1. And then 7 becomes the cutoff because everything between 7 and 8, the ceiling takes us up to 8. 1/3 power gives us 2. But that's going to end up in this next integral, as we'll start this one at 7. And then for the upper bound, we'll go to 3 cubed minus 1, which is 26. So doing it this way on every integral all the way to infinity, that means in this example here, within each integral, we're going to end up with integer values. It's going to simplify just down to an integer, and it's going to be this value right here. So you'll have 1, 2, 3, 4, etc. But here I'm just using 1 over 3 because it's easier to show it, it's easier to visualize. But what we want to do is we're just going to do the exact same thing that we have here, but we're going to do it back on our integral with 1 over 2024. Okay, so now we have this broken up, and of course this is going to be an infinite number of integrals, but at least we've gotten rid of this denominator, just simplifying it down now to an integer value. From here, what I want to do is I want to just generalize and look at one of these, any one of these. So what we can do is we'll just say this is going to be going from a to b. Each of them is going to be cosine pi floor of x over this integer n value that we have in each of these. But now this n value is just a constant with respect to x, so I can bring this out in front of the integral. We can have a 1 over n in front. But now from here on this integral, what I can do is the thing that I wanted to do originally, which is break this up on integers. And keep in mind, we know that the way we have this split up, a and b are already going to be integers for our starting points. Then to break this up, we're going to have our 1 over n in front of everything. And then what's going to happen is we're going to have like our first one's just going to go from, we could say a to a plus 1. And then in our cosine, the floor is going to round this x down to the lowest value to the lower bound. So this is going to become cosine a pi. Then for this next one, we're going to be going from a1 to a plus 2, and then this is going to be cosine a plus 1 pi here. And then this it's not gonna go on forever. This is gonna go on to all the way to b. So I'll just write in the last one like this. And so for this one, the floor is gonna round us down to cosine b minus 1 pi dx. But on this thing, we're gonna get a lot of simplification because just notice we have this all with integer values, and an integer value coefficient on cosine of pi, that's always gonna give me minus 1 or 1. What's gonna happen if a is even, then this is just gonna be 1. If a is odd, like cosine pi, this is going to be minus 1. So basically with everything going on here, it's really just going to depend on if a is odd or even, and it's going to either look like 1, minus 1, plus 1, minus 1, etc., or it's going to be minus 1, plus 1, just starting with a minus 1, and basically the same exact thing. But with either of these cases, basically what's happening is you're going to be getting a whole bunch of zeros, right? Like here, this is 0, plus 0. Now, one thing we notice is we've got different parity on our lower bound and upper bound. So we're never going to get 0 for the whole thing. We're going to have an odd number of terms. And so what we can do essentially is cancel out everything, because all this is going to be 0. All this is going to be 0. We just get one term. And that's going to be based on if a is even, we get this case. And if a is odd, we get this case. And so what that allows us to do with all these integrals here is we just cancel off everything but the first one, because only the first one's going to stay. I mean, you could do it a different way and take the last one, but it's kind of easier for me to just choose the last one and say it all boils down to this. But then each of these first integrals are going to be really simple too, because we just have a constant value and we have our bounds differing by 1. Let's just show it. So if we're integrating 1 dx from a to a plus 1, we get x evaluated from a to a plus 1. When you do that, the a's cancel and we're just left with 1. Doing the exact same thing for the odd case, when a is minus 1, that's just going to change the solution to minus 1. So now coming back to our problem where we left off over here, for all these, we're still going to have this 1 over n in front, which is the same as this value in the denominator. But everything else is just reducing to this plus 1 or minus 1 value. And we know the parity on each of these. We know that the first one starts at 0. 0 is even. So for our first one, the whole thing on here, we're going to have just a 1. And then this term, because this is even minus 1, this here is going to be odd. So all this stuff is going to be just a minus 1 over 2. The next one's going to be even again. That's going to give me a 1 over 3. So what we can do is boil this whole thing down to just the alternating harmonic series. Okay, so again, we've got our alternating harmonic series here. I just have it written out both ways in the sum notation, where this 1 over n is what we found originally from here, and this alternating sign is just coming from this here, the odd and even of the lower bound here. And so when we write out a few terms, we just get 1 over 1 minus 1 over 2 plus 1 over 3 minus 1 over 4 all the way to infinity. But this is a well-known value, and we can just write down the solution for the alternating harmonic series, and this is just going to be ln of 2. Okay, there you have it. Tricky problem from UNSW 2024. Thanks everyone for watching. Have a good day.